stuff up front.
Well, I already had it before, but I didn't know.
No, it's just on the top. Okay, so let's talk real quick. Today you should have done quiz 9.5. If I'm not ever here, make sure you go to Canvas, and that's how I'll be getting track of what's going on. Any lecture while I'm not here will also be up there. So if sub can't get it to work, you're still held liable because it will be up on your Canvas account. Okay, lab notebooks are due today. We are going to finish, I'm hoping in this class we're going to finish the lecture. We almost made it through last time, but I think you guys are a little bit, pay attention a little bit better. You picked up as you came in a buffer lab, so I want to make it through buffers so that you understand what's going on when you come next time for buffers. Like I said, lab notebooks are due today. That's the last thing that goes on this term. Quizzes and sapling will go on next term, and the test for this unit will go on next term. Okay, let's talk really quickly about the lab so that you sort of know what's going on. I'm having the same questions over and over again, so I want to try and stop them right now so I don't have to answer them over and over again. As we look at these acids, and we're looking at these acids on here, come on, pick up. This area right here is an acid group, right here, here, and here. It's not going for me. Let's see if I can bring it into Ink Tools, if it'll let me do it now. Okay, here, here, and here. Those are acid things. So for citric acid, which is your pineapple juice, P, it's not going to let me, you're going to use 3. And that's a lovely 3. Try again. It does not love this. This is 3, okay? On this one, there's this group and this group. So this one, you're going to use a 2. And this one, I love this 2. That's a 2, by the way. Okay, this tartric acid is for grape juice. So this is your grape juice, 2. Okay, this one also has 2 groups here and here. So you're going to use a 2 for this. And this is your apple juice. Okay, so that's how you tell acids in organic. Now, let's go down here to where everybody's asking me the same questions on this part right here. So this you should be able to get from your graph. Your initial pH is where did you start. Final pH is where did you end. This right here is where I had you find the pH equal to 7. That was when I had you do the interpolate. And you actually are going to write the milliliters of NaOH right here. Okay? You're going to write those off your graph. Then for this next part, for pineapple, I'm just going to write through with pineapple. I'm going to assume, you know what happens when you assume, but I need a number. Okay? I'm going to assume that I got this many milliliters, just so I have something to work with. I'm going to take that 11.48 milliliters, I'm going to change it to liters. Okay? By just dividing it by 1,000. Once I've got that, this becomes liters. So I'm dividing by 1,000. 1, 2, 3, so I get 0.01148 liters, right? I'm just going to keep going across here so we have enough room. I'm going to times that by the 0.10 molar NaOH that I used to titrate it with, because I want to find out how many moles I used. That is going to give me moles of NaOH. I'm not going to stop and actually do the calculations here. At this point, that's when I use those numbers we just talked about in the front. Since it was pineapple juice, the number I needed was 3. So I'm going to take this and I'm going to divide it by 3. That will give me moles of acid. Okay? Then to just find concentration, I'm just going to take that moles of acid and I've got to divide it by the 5 milliliters of acid that I used. Okay? But this needs to be into liters, so I'm going to take 1,000 milliliters, 1 liter, whatever that is, that's what I'm going to divide. My units will be ending in molarity of the acid. And that would be citric acid for the first one. Okay? So that would be citric acid, yes. Because up here, at the very top, there were 3 acids on citric acid. So when I went to balance it, I needed 3 NaOHs to balance that out. So that's I had to divide it by 3 to get back to how many moles of acid did I have. Okay? So once I get this answer, whatever it is, okay, then I'm just going to call this answer X circle molarity. I'm going to go in the back and I'm going to figure out how many milliliters of pineapple juice, and I'm just going to take a bogus number, 128 milliliters, they say is my serving size for pineapple juice. I'm going to change that to liters, just like I do all the time, because I've got to have it in liters. Okay, so 0.128 liters. I'm going to take that and I'm going to times it by that X that I just had, molar of acid. Okay, that will give me moles of acid. So then I'll have moles, some amount of moles of acid. Then I've got to add up how many grams per mole there are in acid. You did pineapple in your pre-lab. It's number 1. You already added it up. So it was like 190 something, right? So that's going to, I'm just going to put 191 because I can't remember the number. You're going to times that out, and that's how many grams of citric acid you're going to drink. Okay? For the others, you're going to have to come back up here. I'm going to erase this real quick. Come on. Maybe I'm not. It doesn't want to erase. Okay, we're going to use green. Each of these little points right here, and it's not green. Okay, each of those are carbon. So as you're doing this, this has 1, 2, 3, 4 carbons. So this would be C4, and then I count how many oxygens, how many carbons. I would add that up to get the mass. Okay? So this is just a shortcut we use in organic. Instead of writing the carbons there, we just use a zigzag. You'll probably see it if you ever get medicine at the store, at the pharmacy. They'll give you a pamphlet, and it has these kinds of things written in it. The things right here, those are carbons. Okay? All right, so that should take you through that lab. Are there any questions on that? Okay, what I would like you to do, yes, ma'am. Right here. That would be back off the juice bottle, back in the back. Okay, I just made up a number. The X is what you got. Let me see if I can bring it. Whoops, sorry. The X is what we got right here when we found the answer here. Okay? Any other questions? We okay? Sort of know what you're doing? Yes?
Well, on that one, what's the divide the mole acid? Do you just divide the 5 by 1,000?
You're dividing the 5 by 1,000. That goes down here on the bottom. You're going to moles divided by liters, because this will be oh, I love this. That will be liters right here. Right here, that'll be liters. So moles divided by liters is molarity. Right? Okay, any other questions? Okay, so what I want to do is, it does not take very much time back there in the back. I'm going to go through up here on the board, view it with your eyeballs so you can see what's going on and what you're doing in the back. So you're going to go back in the back. You're going to get a test tube rack. You're going to get 5 test tubes. You're going to get 0.1 molar acetic acid. Whoops, try it again. It has been one of those days. Nope. HC2H3O2. There we go. Okay, so you're going to get that much. You're going to put in each one of these 2 milliliters. So you need a graduated cylinder. And I know it says to rinse it out after. It's just so it's clean. So you're going to grab a graduated cylinder. You're going to put 2 milliliters in. Once you've done that, please put this back because there's not enough of these to go around. Or you can pour this out. This is an acid, so it could go in the red beakers. Okay, so just pour some out. Whatever you don't use, pour back. Once that's done, there are 6 different indicators back there. You choose 5 of them. I don't care which ones you use. Maybe here I'm using universal indicator. Maybe here I'm using bromocresol blue. Maybe here I'm using, I don't know, the red one. Blah, 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 what. Okay, I put 1 to 2 drops in each one. I would probably do 2. Okay? And I write down in my paper, this is what color it is. Okay, initial color. Some of them will change color more than once. If they do, just go this color, then this, then this, then this, even though it has only initial and final. You'll want to know that it changes more than once. Universal will be one of those. Okay, Then you're going to take a micro pipette. That's the ones that look like this. There's one line right here. You're going to get a little beaker. This is your blue beaker that we love to have blue. You're going to get some 0.1 molar NaOH in there. I know it says to measure it out. Just get you a beaker full of NaOH. Okay? You're going to fill the NaOH up to this line, and you're going to put it in here with the 2 milliliters, and you're going to swirl it, see what happens. You're going to do this 3 times for each test tube and see what color it is. So you're going to do it 3 times here, 3 times here, 3 times here, 3 times here. Write down the color. Once you're done with that, you're done. Clean it up, get a stamp, you're done. Come back in here. I want to be back here sitting in here by 25:2. Questions? Yes?
So are you putting 3 of the pipettes?
3 pipettes up to this line. No, 1 at a time. See if it changed, see if it changed, see if it changed. Okay, any other questions? Okay, let's go. Goggles mandatory. Molecular equations, net ionic equations, and ionic equations again. We're going to talk about K's again. So a lot of this we've already done, but we're going to do it specific towards acids and bases. So don't forget that your lab pH, that's a home pH lab, needs to be included. You should have 3 labs coming in today. Your pH lab, your first titration lab, and this beverage lab. Okay, 300 points. So going forward, we're going to talk about salts first up. Salts have several definitions. A salt is basically has a water molecule associated with the ions in its crystalline structure to some extent. A salt is made from an acid and a base. The acid part of a salt is the anion. The base part of a salt is the cation, or the positive ion part. When we have a water of hydration, that just means that waters are attached. They're not necessarily part of the actual structure, but they're sort of attached, sort of like a balloon is static to a person as they're trying to walk on those games where you try and keep a balloon static to you. An equivalent of salt is the amount that will produce 1 mole of positive electrical charge when it's dissolved and dissociated. So if an ion becomes a positive 2, that gives twice as much equivalent. So that would be an equivalent of 2. So to get a 1 mole of equivalent would just be to get a +1 ion. Okay? And these are just some definitions. If you don't get these all down, you can look at it again on Canvas, or you can look in your book and pick them up for the definition. Pretty simple and straightforward. Okay. So we have several reactions that yield salt that you need to be familiar with. Hint, hint. Okay. One is an acid plus a metal. When we have an acid plus a metal, we're going to get a salt and hydrogen gas. So if I have battery acid and I accidentally spill it inside my car where the metal is, the metal iron is going to react with the acid. I'm going to get some bubbling going off. That's hydrogen gas, and I'll be left with a salt with no iron to hold my car together. Okay, so that's bad to do. If I have an acid and a metal oxide, that would be like calcium oxide or sodium oxide or magnesium oxide, then what I'm going to get is salt and water. If I have salt and a metal hydroxide, hydroxides are where our strong bases are, like lithium hydroxide, sodium hydroxide. We're going to end up with salt and water. This is a strong acid, strong base kind of reaction. We're going to get a neutralization. If I have an acid plus a metal carbonate, this would be like calcium carbonate or barium carbonate or sodium carbonate. I'm going to get salt plus water plus carbon dioxide. You would think you'd get carbonic acid, but carbonic acid does not stick around very long at all. So we always write carbonic acid as H2O and CO2. Okay, we don't ever write H2CO3 because it really doesn't exist. Okay, if we have an acid plus a metal bicarbonate, this would be like sodium bicarbonate, like baking soda. We actually get the salt, the water, and the carbon dioxide again. This is what we use in baking so that we can get things to raise, like bread dough. And if we're not going to use yeast, we use sodium bicarbonate. So things are not flat. Okay? So these are reactions that you'll be held for, so you need to make sure that you are familiar with them. Okay, so in order to be able to write these equations and know where these salts come from, we've got to think backwards. And we've done this before. What ions are lithium chloride, what is lithium chloride made up of? Lithium, Li+, right? And chlorine, Cl-. What did I tell you? What one came from the acid and what one came from the base? Positive is the base, so this one would come like LiOH. So this positive is where my base comes from. The negative ion is where my acid comes from, because remember, hydrogen's a positive ion, so it has to go with a negative. So this is where my acid would come from. Now, I can look at these and say, okay, I had a strong base and a strong acid, because these were one of the 6 strong acids and strong bases. So lithium chloride is going to be about a pH of 7. It's going to be neutral, because I have a strong acid and a strong base is where it came from. Okay, so let's look at the B. What would be my base that would come from B? Copper hydroxide, right? And what would my acid be? HNO3. Okay, are either one of these strong? Nitric acid is one of our strong acids. So this one is strong, and this one's not one of our strong acids, or bases, is it? So because the acid is strong, but the base is not, this one is going to be a pH less than 7. Okay, so let's look at the next one. What's my base going to be? Potassium what? Hydroxide. Now I'm making this mix with water, because salts will mix with water. So water splits into H and OH, right? So that's why I'm getting the OH for the base and the H for the acid. So what would the acid be? It'd be H3 or H2PO4, depending on how many H's that I'm going to move off. We'll just call it H3PO4. Are either one of these strong acids or bases? Potassium hydroxide strong. Is the phosphoric acid strong? No. So this one is a strong base. So because of that, this one is going to be above 7 as far as a pH when I dissolve it in water. Okay, let's look at the next one. What base am I going to get? Calcium hydroxide. What acid am I going to get? Carbonic acid, which really, water and CO2 if I go backwards. Okay, so are either one of these strong? Calcium hydroxide is a strong base, so this one is going to be a pH above 7, right? Okay, let's look at the next one. Magnesium, what's it going to go? Magnesium hydroxide, right? So we're going to add the OH to it. And we're going to get acetic acid. Okay, either one of these strong? Neither one of them is strong. So here we're going to be, we don't know. This was actually a little bit stronger, so we're probably going to be above 7, but it's iffy. It could go either way. This is more like what we're going to get into with buffers. Okay, because we need a weak acid and a weak base. And this is sort of what we've got going on there. Okay, let's look at the last one. K what? OH and HNO3. What do we got? Strong acid, strong base, so the pH is going to be about 7. Okay, see how easy this is? Everybody okay? What do we need to know in order to do this? Our 6 strong acids. Remember the SWOOT. HNO3, H2SO4, HClO4. That's our oxy acids. Those are in the SWOOT. Then straight down, HCl, HBr, HI. 6 strong acids. Our bases start at lithium, go lithium, sodium, potassium, slide over, calcium, strontium, barium. It's Tetris pattern. Okay, if I know my 6 strong acids and bases, everything else is weak. All right? Okay, so going forward, Now we've got to be able to write the equation using those equations that we had learned about beforehand. So I'm going to make this salt, but I'm going to make this salt using a solid that's an oxide. Okay, so the solid that's an oxide is going to have to go, oxide is going to go with what part of that, the copper or the chlorine? Copper. So copper here has a +2 charge. That means the oxide is going to be CuO, and that's going to be my solid, right? What is my acid that's going with it? What's the other part? Yeah, just HCl. And it's a strong acid, so it's going to split, so it's going to be AQ. Solubility rules, copper chloride, soluble or not? Soluble, it's a chloride. Chlorides are soluble, except for PMS, lead, mercury, and silver. I'm missing something. What am I missing in this equation? Outsides, insides, what's missing? H2O is missing. And H2O is a liquid. What else needs to be done with this equation to be finished? Balance. What do I need to do to balance it? 2 there, done. Okay, let's look at the next one. I'm going to make magnesium sulfate soluble or insoluble? Sulfates are soluble except for castor bear, right? So this is AQ because that's not castor bear. Okay, it says it's solid in a carbonate. What's carbonate, positive or negative? It's -2. CO3 is a -2. So it's going to have to go with what? Magnesium or sulfate? Magnesium. Magnesium's a +2, carbonate's a -2. Put it together. And it said it was a solid, so I'm going to put an S here. What is the acid that's missing? Sulfuric acid, good. H2SO4, strong acid or not? Strong acid, so it's going to be AQ. It's going to split. What am I missing over here on this other side? Careful. Inside, outside, but this one had a trick. So we did the insides to make magnesium sulfite. The outsides are going to make what? Carbonic acid, which quickly, water and carbon dioxide, quickly decomposes. You got to recognize that. CO2 and water. So CO2 is a gas. Okay, last one here. Lithium bromide. Soluble or insoluble? Group 17 is soluble, so AQ. Okay, I'm making it from a solid hydroxide. What goes with the hydroxide? Lithium. So I've got LiOH. Basically, I'm making sort of like, whoops, that's a solid. Sort of like we did with the NaOH, making a solution. Okay, what is missing? Yes? No, I could put the lithium hydroxide first. That doesn't matter. Okay, what else is missing? Hydrobromic acid, good, HBr. Is this soluble or not soluble? Soluble, it's one of our strong acids, good. What's missing on the other side? H2O. And I forgot to say, did we balance all these others? I didn't look at the balancing on the second or the third one. It looks like they're balanced. H and OH. Okay? All right, going forward, now we're going to talk about equivalents. Equivalents are all about charges. So how many charges do I get per mole of stuff? Okay? All I'm looking at is a charge on the positive or the negative. If I'm only given the negative, then I look at the negative. But if I'm given the positive, that's what I look at. Okay? So if I have a plus or minus 1 charge, doesn't matter if I'm looking at chlorine or sodium, I can just say 1 gram equivalent for chlorine is this, 1 gram equivalent for sodium is this. If I have a +2 or -2 charge, then I've got to take that mass and divide it by 2 to get a gram equivalent. Okay? So I'm just going to take and divide it by. So molar mass of the ion divided by the charge of the ion. Done. Okay, real simple. Don't make it too hard. There will be a couple questions like this on the test. Okay, so don't make it too hard. Okay, so going forward, equivalence is just the charge. Equivalents are just the charge. If they ask for milli-equivalents, how do you go from equivalents to milli-equivalents? Times by 1,000. Okay? All right, so here we go. We've got a 0.1 mole. We're supposed to determine the number of milli-equivalents in each of these. So what I would do is I look at the charges here. Okay, plus 1, minus 1, right? So then I say, okay, for each of these moles, in 1 mole of Ki, there is 1 equivalent of Ki. Done. 0.1 equivalent. Okay, what about the next one? This is a plus 2, right? 1 mole, 2 equivalents. Done. All I'm doing is timesing by the charge on the positive ion. Okay, so the last one, what do I do? 1 mole, how many equivalents? 3 equivalents. Done. Okay? We all right? Okay, quite simple. Okay, now what happens if they don't give me moles, but they give me grams? So we're going to determine the number of equivalents and milli-equivalents in 5 grams of each of the following salts. So first thing I need to do is add up the salt. This is what you need to know. This does not mean times. That means it's attached like a balloon's attached. I still have to add it. So I would take 2 times 22.99 plus 12.011 plus 3 times 15.999 plus 10 times, I know water's mass is 18.015 because I've added it up so many times. Okay, get that mass, whatever it is. Okay, so I'm just adding it up. This does not mean times, it just is I'm adding it to it. Okay? So once I've got that mass, I'm just going to call it mass X. If somebody gets it before we move on, that's great. I'm going to take those 5 grams of that, and I'm going to say in 1 mole, there are X number of grams in that mole. Everybody okay with that? What's the charge on the positive ion? Plus 1. So in 1 mole of this, there's 1 equivalent of sodium. And I've got my equivalents. If they asked me what the equivalence of carbonate was, then I would do the minus 2. Okay? Or the 2, sorry. Now, to get to milli-equivalents, once I got this answer, I want milli-equivalents times it by 1,000. Okay, way easy, right? We're okay? Okay, this is just as simple. I'm not going to go through it because we're running out of time. Is it okay? Whoops. Must be because we already went forward. Is everybody okay with that? Is there anyone not okay? Okay, we're going forward. Okay, so now we're going back and we're sort of reviewing. What's a titration? What are we trying to do in a titration? We're trying to find an unknown molarity of an exact amount of stuff, right? Using something that we already know the concentration of. So a technique where a solution of known concentration is used to determine the concentration of unknown solution. Typically the titrant, the known is in the burette. That's what we've been doing, right? And what's called the analyte, the unknown, is in the beaker or the Erlenmeyer flask at the bottom. Okay? The equivalence point, a lot of kids are asking me, what is the equivalence point? That's where your pH is 7, where your acid and your base are equal. Okay? That's not necessarily the end point. When we did the quick, dirty titration, remember the really quick, dirty titration where we didn't use the pH probe? That one, we found the end point. The end point is when the indicator changes color. Okay, it might not be the exact same as the equivalence point, because if my equivalence point doesn't go in that sharp up curve, so here's my, if my 7, pH of 7 is not in this point and maybe my indicator like phenolphthalein changed right here, it's off just a little bit. Okay, does that make sense? Or if I chose another indicator like bromocresol blue and maybe it changed down here and I wasn't even close. Okay, so the indicator can change at different pHs. I've got to pick an indicator that will change during this fast jump. in my titration in order to get my endpoint and my equivalence point to be almost the same. Does that make sense? Everybody understand the difference between endpoint and equivalence point? It's important. Okay, so we use indicators. We just did a little bit of love on indicators. And indicators basically have a different color over here than they have over here. And as I add hydrogen or take hydrogen away, it shifts the color of the indicator. That's all that's happening. Okay, endpoint is when the indicator changes color. So these are usually weak acids or weak bases that we're using. And they just display different colors. We did a home graph where I sent one of these home and said, okay, acid is red, base is blue. You're going to use pH paper. You're going to figure out what things are, right? We also, so here's your pH paper we sent home. We've been using pH meters in class. These actually work on electroconductivity on how many ions of positive are in the solution or negative are in the solution and how well it conducts electricity. Okay, we can be able to find how many moles do we need to neutralize something. So on this one right here, we would take this, divide it by 1,000 milliliters to get it into liters. So it would be 0.450 liters. Everybody okay with that? Times it by molarity, 1.4 molar, gives me moles of HCl. And since it's a one-to-one relationship, what does that tell me? My moles of HCl will equal my moles of KOH. So whatever I end up with there is the end. Okay? Now, in the last lab, where I walked you through the pre-lab, I took you step by step. Why did I take you step by step? Because it was not one-to-one, right? Because we had tartric acid, and we had citric acid, and we had malic acid, and tartric and malic acid had we needed twice as much base as we did acid to make them balance. And for citric acid, we needed 3 times as much NaOH as we did acid to balance. So that's where we would play here. But we have to get to moles of one before we can go to moles of the other one. Does that make sense? We can do the same thing here that we did up here. Everybody okay with that? I'm not going to do it again if we don't need to. Okay. So we talked about strong acids. We talked about strong bases. Now we need to talk about weak ones. Weak ones are when we have less than 100% ionized in water. Usually they're between 1 to 5% ionized. We used one today, and that was vinegar, which is acetic acid. Acetic acid is a real known weak acid. I will want you to write it like this, though. This is the organic or inorganic way to write it. What is written up above is the organic way to write it. So we'll be writing it HC2H3O2. So you can see that that one hydrogen does come off. Okay, that one hydrogen comes off because this section right here is the acid part of any organic compound. And this is the hydrogen that's going to come off. Okay? All right. When we look at weak bases, the most common weak base is probably ammonia. And ammonia will gain a hydrogen and become ammonium. And that other hydrogen will come in right here. Okay, and take that place. So as we look at other possible weak bases, caffeine is a weak base. Phosphate ion is a weak base. Benzoate ion that's found in Coca-Cola is a weak base. So we've got a lot of different bases. When we talk about amphoteric, I'm talking about something that could act as an acid or a base depending on who it's with. Water is one of those. Water can act like an acid or a base depending on who it's with. If I have an acid and it has more than one hydrogen that can be given off, if one hydrogen's already gone, then it can act as an acid or a base. So sulfuric acid, if one hydrogen's gone, can act as an acid or a base. Phosphoric acid, if it has lost 1 or 2 hydrogens, it can act as an acid or a base. It just depends on whose company they're in. As we're looking at Ks, we can write a K for acids and bases. When we write it for an acid, we call it Ka. We still do it the same way we wrote Ks before. Products over reactants to their exponents, for their coefficients as exponents. Same way. If the Ka is less than 1, I've got a really weak acid. If it's greater than 1, I've got a really strong acid. Remember, products on top. So if I've got a lot of products and it's an acid, then I've got a strong acid, because that's what it means by splitting. If I have a base, then I call it Kb. Okay, so this is not hard. Again, if the Kb is small, below 1, then I've got a weak acid or base. If it's above 1, then I've got a strong one. We end up with a chart that looks like this. Now, if you times the Ka times the Kb, you will get the Kw. So Ka times Kb equals Kw. Okay? If I have a strong acid, the base of that is weak. If I have a strong base, the acid of that conjugate acid is weak. So a strong acid goes to a weak base, a strong base goes to a weak acid, and vice versa. Okay? That's just basically what that says. Okay, some acids donate more than 1 proton. If it only donates 1, it's called monoprotic. If it donates 2, it's diprotic. If it donates 3, it's triprotic. If it donates more, it's called polyprotic. We have a lot of organic acids that are polyprotic, okay, that can donate more than 1. And that hint right there is just in the first part of it. Okay, protic is just proton. All right, so this is going back to our molecular ionic and net ionic equations. We can do that for acids and bases. Remember that the net ionic equation for an acid and a base is usually OH plus H yields H2O. Unless it's a weak acid or base, then you're going to have that weak acid or base in the net ionic equation because it will not split. Okay, it will not split on the other side. So if I have phosphoric acid, which is a weak acid, it actually splits down, and each time we could actually do one more where we take the last hydrogen off. But we can then do an ionic equation and split it. And then we could do the net ionic equation, which we would still get the 2's, but the 2's would go away and we still end up with H plus OH yields H2O. Okay, as long as we show all the possibles. Okay, now, almost there. Okay, so Ka values, we need to be able to look at them and say which one's the strongest, which one's the weakest. This will be like a problem on the test. So how do I tell which one's the strongest? What's the biggest number on here? Remember, biggest number has the lowest negative, right? So C is the strongest. What's my weakest? A. Okay, you got to be careful because they have the same exponent, but you got to look at the front numbers in front. So you need to be able to arrange that. So you just said that C was my strongest acid. So it's going to be my weakest conjugate base. What's going to be my strongest conjugate base? A. Okay? So you got to be able to look at the numbers and be able to flip them. Just remember, if it was strong acid, it's a weak base. If it was a weak acid, it's a strong base for conjugates. Okay, so we should be able to write a Ka for any of these. So hydrofluoric acid, HF, goes to H plus F minus. These would be AQ, AQ. This would be AQ, but it really won't go much. And remember, our Ka is just the products to their exponents over the reactants. Whoops. I really wanted a K in there, sorry. So you should be able to write that for anything that's given. Pretty easy, right? Do you have any problems with that? Just products over reactants to their exponents. For usually Ka and Kb, we won't have exponents because we're just moving one hydrogen off. Okay, yes, did you have a question? Okay, I'm just going to pop forward, is that okay? Do you know what hypochlorous acid is? This HClO. Okay, so if you don't know what that is, you can put it in. Okay, looking at the pH, you should be able to, very quickly, what's the strongest one on there? Acid. D. D. D is my strongest acid. Which is my strongest base? C. Okay, so really quickly, you should be able to line those all up. We okay with that? Acid is strongest base. Okay, as we get in here, salt hydrolysis is just adding water to the salt. We've already done that. So this was just another look at how to do that. Finding which was the acid, what was the base, whatever. And we've done this already at the very first. I'm going to leave that for you to practice on. Okay? Now, this is what I was trying to get to, buffers. Okay, so a buffer is a solution that resists pH changes. We actually have 3 buffers in our body to keep our pH at a certain level. If we don't keep it at a certain level, we die. Okay, we only have a very little leeway that we can move our pH. So a buffer, if I add acid or if I add base, will maintain that pH at a certain point until I break the buffer. So we're going to do a buffer lab next time, and it's going to stay at basically the same pH for a long, long time, and all of a sudden it will go boom and be up here. That's when I broke the buffer. It doesn't go gradually like we've seen and then go up and over. It goes straight, 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 boom, bam. Okay? Buffer capacity is just that. How much acid or how much base can I hold? Now, this next part is where you need to make sure you get this written down. This is what's called the Henderson-Hasselbalch equation. We are going to be using this. This right here, I had some that were struggling with this in the pre-lab for the buffer. pKa is just taking minus the log of the Ka. That's it. Minus the log of the Ka. Anytime you put a P in front of anything, it's minus the log of it. Okay? Anytime you put a P in front of anything, it's minus the log. So don't shoot at the log. No, anyway. We'll just go with that. Okay? All right? So conjugate base over conjugate acid. You'll have some pre-lab that you'll need to be doing that. I'm going to have to stop right there, and we'll actually go through these problems next time. But you do need to know that equation to get your lab pre-lab done. Okay? I feel like I've been through a marathon. I'm sure you do too. We'll see you next time. Be ready to do that buffer lab. Yes?
So, you want me to just put that in?
Sure. Why wouldn't I?
Well, I don't have my other
No, don't put it in the bin. Bring it tomorrow morning.
So,
I don't want to grade it twice.
if you're going to divide by 3, don't you have to times by the moles of the space?
No, this is how much NaOH you have. So you're dividing by 3 to get the moles of the acid.
But
You needed 3 times as much NaOH to balance 1 mole of acid. Let me stop this so I don't have this.